This is CS1101, lecture 7.2. Today we're going to be talking about assertions, and then we're going to be adding on to what we've said previously about style and introducing the JavaDoc. So first we'll talk about assertions. So consider the following code. Just a simple if statement. If x is greater than 3, we're going to decrement x, else we're going to increment x. And notice the locations in code point A, point B, and point C. With our discussion of assertions, we're going to be talking about things that are true at point A, B, and C. So let's ask the question, what do we know about the value stored in x at each of the points A, B, and C? Can we make any assertions? Can we make any guarantees about the value of x? And these guarantees should take on the form always, never, or sometimes. So, at each of these points, what can we say about x is greater than 3? Is it always, never, or sometimes greater than 3 at point A? In this situation, at point A, x is always greater than 3. Because we are inside of and directly beneath a test. The only way we can get to point A is if it is true that x is greater than 3. So this specific situation we can say always. What about at point B? Is x greater than 3? Always, never, or sometimes? Never. The only way that we can possibly get to this else statement and to the location that we're at where this comment point B is if x is explicitly not greater than 3. What about at point C? Can we say anything about it? Well, how can we get to point C? We could have gotten to point C by x being less than 3 and then adding 1 to it. But how much less than 3? Maybe x was equal to 1. So if x was equal to 1, then when we do a post increment on x, at point C, x is equal to 2. However, if x was 5, then we would decrement x, and then when we get to point C, x is 4, in which case x is greater than 3. So in this case, we would have to say sometimes. This is a helpful line of thinking to apply to code, to ask yourself, what can we say for certain about a specific point in the program? What do we know if we are here? So let's continue to do this sort of evaluation. Look at the comments at point A, point B, and point C, as well as point D, and see if the answer to the questions following at the end of the comment is always, never, or sometimes. Okay, point A, is number less than 0.0? Number comes from the console, so sometimes, right? Because it depends on what the user typed in. Maybe the user typed in a number less than 0.0, maybe they didn't. It'd be impossible to know. So sometimes at point A, number is less than 0.0, but not necessarily. What about at point B? Is number less than 0.0? Well, point B is hiding behind a test for a while loop. So the only way we could possibly get to this point in the code is if number is in fact less than 0.0. So we would have to say always. At this point in the program, at point B, number is always less than 0.0. Okay, what about point C? So here, we are again getting a number from the console. So that means that we don't know. Maybe it is, maybe it's not. So we have to say again sometimes. What about point D? At point D, is number less than 0.0? How could we get to point D? To get to point D, we have to go through this while loop. To exit the while loop, this test has to be false. The test is number is less than 0.0. If that's false, then at point D, number is less than 0.0 is never true. So this would be never. Notice what this code is doing. The user has been prompted for a non-negative number, and they've typed something in. But based on our assertions, we can tell we actually don't know if they typed in a negative number or not. They may have typed a negative number. But when we enter this loop, we know that they had typed a negative number. So if this test had failed, when we get to point D, we know that we are no longer dealing with a negative number. However, if the original number they typed in was negative, then we will again prompt them and say, nope, that's a negative number, try again. And we'll get a number from them using the console, using a scanner. And we don't know if they typed in a negative number or not, but we're in the middle of a while loop, so we're going to come back up here and test. If the number is not negative, if it's not less than 0.0, then we will exit the while loop and go to point D. So what we've done here is we've instituted a method to be able to know whether or not at point D we're guaranteed that the number stored in the variable number is non-negative. So this loop is an input validation loop. It's a loop that allows us to get a number from the user and guarantee that we have a positive double value. So there are a few special situations in which we're able to know something about the value stored in a variable. One of those is immediately after initialization. So if we were to look at the initialization of x equals 3, immediately after it's initialized, we can guarantee that x is equal to 3 or x is greater than 0. Anything, we can guarantee any particular thing about x because it has not been changed. The value stored in x is entirely known. So x is greater than 0 always at this point. But typically you would know nothing about a parameter after its initialization. So when a parameter is passed into a method, we know nothing about whether or not the value has any particular, or the variable has any particular value. So if we were to ask the question, is a equal to 10, we would have to say sometimes. No matter what we test at this point, we have to say sometimes. Because there's no way to know what the programmer has passed us as a parameter. Maybe they followed our desired preconditions, maybe they didn't. Another place that we can know something about the state of a variable is inside of an if statement or a while loop. Hopefully you know why, and that makes sense to you, because when we perform a test on a value, we are able to know that if the program gets to the interior of this if statement, a is definitely less than 0, so therefore we can say for certain that a is not equal to 10. We can do something similar with while loops since they also possess a test very similar to an if statement. At the beginning of a while loop, there is a test just as there is at the beginning of an if statement. So if the test is y is less than or equal to, well, it doesn't say less than or equal to, if the test is y is less than 10, and then we want to know if we can assert y is less than 10 inside this while loop immediately after the beginning of the loop, then the answer is yes, always. Otherwise, we would not have gotten into the interior of the while loop. Immediately after the loop, we also know something about it, because we would not have been able to exit this loop if the statement had not been false. So therefore, immediately after the while loop, we are capable of guaranteeing that y is in fact not less than 10. Notice though, inside the loop's body, we may change the value in the variable such that we're not able to guarantee what the value is. So for instance, when we entered this while loop, we knew that y was less than 10 at this point in the program. However, immediately afterwards, we add 1 to y. Now notice, we didn't know the exact value of y, we simply knew that it was less than 10. So when we add 1 to y, we don't know whether or not y is still less than 10. It may, in fact, now be equal to 10. So, is y less than 10? Sometimes. There's another situation that can trip you up when you're attempting to make assertions about different locations in a program. Remember that a loop may execute 0 times. So, for instance, in the following method, you may think that we could make some assertion about the value of x after this while loop. The reason you might think that is because you would say, well, we have initialized x to be equal to 0, then inside the while loop we have incremented x, so on the outside of the while loop we must have it be true that x is greater than 0. However, what may have occurred is the user may have passed a value into y that was less than 10. If that occurs, we will never enter this while loop, and instead we will jump to the line immediately after the while loop, in which case the value of x is 0. So remember how programs execute. Be able to trace through the program's execution and know how the flow of the program is going to occur, because without being able to do that, you're not going to be able to make these definite assertions about the state of variables at different places in the program. So we've discussed different places in a program where we can say something for certain about the value of a variable. So after it's initialized, inside of a while loop, immediately after a while loop, or inside of an if statement. However, are there situations where we know for certain we will not be able to say anything about the value, other than sometimes? Yes. So anytime we read from a scanner, we are not going to be able to say anything for certain about the value returned from the scanner. A parameter's initial value inside of a method is going to always have a sometimes answer for any assertions, because we don't know what someone is going to pass to the method. And anytime you read a number from a random object. So all of these situations introduce uncertainty to the code, and for that reason we can't say anything more than sometimes if we attempt to make some assertion about the value of the variable. Essentially, if you can think of a way for the assertion to have both yes and no as an answer, depending on the values stored in the variables, then the answer should be sometimes. So in a future lecture, we will introduce assertions not simply as a logical approach to programming, but as an actual statement in Java that can be used to debug and test your program. But for now, assertions are a way to think of the program in terms of, if I get to this line in the code, then the value in the variables must be, and then whatever you come to and understand that they must be. So always, never, or sometimes equal to, greater than, or less than a certain value. Here's a mini exercise. At each of the locations in this code, give the assertion the proper value. That is either always, never, or sometimes. Always, never, or sometimes. So see if you can ascribe the correct value to each of these assertions. In the first upper left-hand corner assertion, we have x is initialized to the value 3. So anytime you have an assignment operation to some literal value, we can make definite assertions about the value of that variable. This has the value always. Okay. We have passed a into a method. Can we make any assertions about the value stored in a? No. Anytime you pass a value into a method, we do not know what value was passed, and therefore we can only say that sometimes a would be equal to 10. Okay, we again are passing a value into a method, but now we're going to test it in an if statement. So we've passed a value into this method. We can say for certain at this point we have no knowledge of the value in a, but then we issue a test via an if statement and say, is a less than or equal, or is a less than 0? So then when we get to this assertion, is a equal to 10, we can say never, because there is no way that we could be on the interior of this if statement if a was 10, because 10 would be greater than 0. So never. Okay, while y is less than 10, and then on the interior of this while loop, notice there are no statements which change the value of y before this assertion. So at this point in the program, is y less than 10? Yes, it always is less than 10 here. Otherwise, we would no longer be in this while loop, and this we would not be at this line of code. So the only way to be at this line of code is if, yes, in fact, y is less than 10. Always. Okay, but what about immediately after we exit the while loop? Is y less than 10? No, because the only way that we could possibly get to the statement immediately after the while loop is if we had the test be false. So we know that the test y is less than 10 results in a Boolean value false. That means y must be greater than or equal to 10. Therefore, this assertion is never. Alright? What if we're on the interior of the while loop, but we're after some statement which changes the value of y? Well, it depends on the test. So in this particular case, we are testing y to see if it is less than 10, but then we're adding 1 to y. So do we still know if y is less than 10? Can we say always or never? No, because what if y was equal to 9? Well, 9 is less than 10, so we would enter the while loop, we would increment y to 10, and now, at this point, where we're attempting to make an assertion, y would be equal to 10. So that's a way in which this would be not true. And a way in which it would be true would be if y had been equal to 8. 8 is less than 10. We enter the loop. We increment y. Y is now 9. Is y less than 9? Yes. So we are able to manipulate the values of these variables and achieve both a yes and no answer. So that means the answer here must be sometimes. And finally, we have a value inside of a method. So we're attempting to find and make assertions about the value of x. We're passing in the value y. So inside here we are initializing x to 0. And then we have a while loop. While y is less than 10, we're going to increment x. then we're not going to do anything else to it. And then at this point in the program, is y greater than 0? Always, never, sometimes. Well, if this while loop executes even once, then x is going to be incremented, which means it would in fact be greater than 0. However, what if we pass in the value 11? Is 11 less than 10? No. So we failed the test. That means we're going to jump down to the statement immediately following the while loop. Is x greater than 0? No. X is equal to 0. So here's the situation where the test would be no. Can you think of a situation where the test would be yes? So if we passed in a value to y of 8, then when we get to this test, y is less than 10. Yes, it is. 8 is less than 10, so we are going to increment x. We assume that we change y's value somehow so that when we come back around, the test fails, and we jump down here. Now, x has been incremented greater than 0, and therefore the answer would be yes. So we have one set of values which gives us a yes, one set of values which gives us a no. That means this must be a sometimes. Sometimes are kind of problematic because sometimes means we actually don't know anything about the state of the variable in that location, or we know very little. We can make no guarantees about the assertion that we would like to provide some sort of never or always guarantee about. Let's do another mini exercise. See if you can identify the appropriate value for these assertions at each of the points in the program. So which of these assertions is true at each of the points in the program? Okay, x is less than y. At point A, we have passed in the value x, we have initialized y, x is less than y. We don't know. The best we could say would be sometimes, because it would depend on what we passed in for x. If we passed in a value that was less than 10, then yes, x would be less than y. However, if we passed in 11, then no, so sometimes for point A. At point B, we have entered a while loop, and the test for the while loop is x is less than y. The only way to get to point B is if x is in fact less than y, therefore at point B, for x less than y, the answer is always. Okay, then we increment x. So at point C, do we still know that x is less than y? No, because x could have been 1 less than y, and now at this point, x is equal to y. On the other hand, perhaps x was much less than y, so therefore at this point, it would still be true. Clearly, we're in a yes-no situation. That means we don't know the answer, and that means this is a sometimes. At point D, is x less than y? Definitely not. The only way to get to point D is if the test fails in the while loop. If the test fails, that means that x is certainly equal to or greater than y. So how about is equal to y? At point A, again, sometimes. Depends on what we pass in for x. At point B, we just did a test to see if x was less than y, so the answer would be never. At point C, it could be true that x was the value 9, so when we add 1 to 9, we would get 10, and x would be equal to y. So sometimes. So we've got sometimes, never, sometimes. And then at point D, again, it may be the case that x is equal to 10. We know that x is equal to or greater than y at point D, but we do not know if it is specifically equal to 10. So it would be, again, sometimes. Let's do one more mini exercise on assertions. So here we have a method called mystery where we're passing in the value x and y. See if we can fill in the table for the assertions on the bottom right. X is less than y, x is equal to y, and z is equal to 0 for each of the points in the program. For x is less than y, at point A, we would have to say sometimes because we know nothing about either value. At point B, we know that in fact x is greater than or equal to y at point B, so we can say never at point B is x less than y. For x equals x minus y, so we're finding the difference between x and y and assigning it to x. And then we are asking, is x now less than y? This would be sometimes, because all we know for certain is that x is greater than or equal to y. So one situation could be x and y are both 0, in which case 0 minus 0, x is not less than y, because that would result in x having a value 0 and y having a value 0, so they would be equal. So no. We don't know anything about point C. We can also contrive other situations such as x is equal to 6 and y is equal to 5. In this case, 6 minus 5 equals 1. Therefore, y is greater than x, or that is to say x is less than y in this particular case. So C is sometimes. At point D, we have not changed the value of x or y, therefore we are still at sometimes. At point E, we are able to say that yes, always x will be less than y at point E. The reason is because to be able to get to point E, this test must fail. X is greater than or equal to y must be false. That means that x is in fact less than y at point E. So our table looks like this. Sometimes, never, sometimes, always. Is equal to y. At point A, sometimes, for the same reason that we said for less than y, because we don't know what was passed in. In the while loop, sometimes, because x may be equal to y, but it also may be greater than y. X equals x minus y. Well, if x had been 6 and y were 3, then x equals x minus y would have x have the value 3 and y have the value 3. So at point C, that's a way that x and y could be equal. However, we've also talked about ways in which x could wind up being greater than or less than. So definitely a sometimes. We're not adjusting the value of x or y at point D, so that is also sometimes. At point E, we would say never, because we were able to say that at point E, x is always less than y, which means it is never equal to y. Okay, for z is equal to 0. At point A, we're able to guarantee that yes, in fact, z is equal to 0, because we have initialized it to the value 0, and we did not do anything in between the assertion and the initialization to change the value of z. At point B, we've still not done anything to change the value of z on the first iteration of the loop. But we can also get to point B on the second iteration, in which case we have done something to the value of z. So we're not asking if on the first execution at point B, if z is necessarily equal to 0. We're asking if there's any way to get to point B where z is not equal to 0. If the answer to that is yes, then we can't guarantee that it is equal to 0. So inside this loop, we are going to adjust the value of z. And we're not testing to see what the value of z actually is, so there's no constraint on the value of z. So at point B, we would say sometimes, because if this loop progresses through and comes back around, at point B, z would be 1. So we actually don't know if z will have the value 0 at point B or not. The same thing goes for C and D. Actually, at point D, we can guarantee that the value of z is not 0. So at point D, we would say never for is equal to 0. But at point B and point C, we would say sometimes. What about at point E? At point E, we would say sometimes as well. Why? Because we may have gone through this loop, in which case we've incremented the value of z and then jumped down. Or we may have failed the test initially and skipped the loop altogether and wound up at point E, in which case z would have the value 0. So A has the value always, B and C, as well as E, have the value sometimes, and D has the value never. So here's a program that prompts the user for numbers until they type -1. When -1 is typed, we exit the loop and we return the maximum of the numbers that have been typed. So this is a sentinel style loop with the sentinel being number equal to -1. And we are going to continue as long as number is not equal to -1. So we have a fence post shape here where we are going to get the first number. Then we are going to test to see if it is the max. And then we are going to get the next number. The reason we use the fence post structure in this particular situation is because when we're dealing with a sentinel style loop, we do not want to include the sentinel value in our potential set of max numbers. So therefore, we need to get n numbers, but only compare and evaluate the first n-1 in our max calculation. So what we're wanting to do here is hopefully we can assert that max is greater than or equal to number in this location. The reason is because we want to return the maximum value typed in. So it should be the case that we can assert that yes, in fact, max is always greater than or equal to number when we return the maximum value. Otherwise, there's something wrong with our code. So let's look at the different locations and assertions we can make in this program. Is max greater than or equal to number at this location? Yes, we have just initialized max to the first number typed in. So at this point, max is definitely greater than or equal to number. Inside the while loop, we only enter if the number which was typed in is not equal to -1. If -1 was typed in at first, we would jump to the end, and max would be equal to -1, so this would be true. Okay, so far so good. But what if we have a number that is not equal to -1, we enter the loop? Is max greater than or equal to number? Yes. At this point, we can say, as long as we got there on the first loop through, yes, at this point, we are greater than or equal to number. However, if, when we progress through this loop, we get another number from the user, and this number then is greater than the current max, when we test again, number is not equal to -1. At this point in the program, now number is greater than max, because the user typed in something that was greater than the current max. So we've described two possibilities, one in which, yes, max is greater than or equal to the number, and one in which, no, number is greater than max. This must be sometimes. In this location in the program, we have an if statement that says if number is greater than max, max equals number. So here, we know that max must be greater than or equal to the number stored in the variable number, because otherwise we couldn't get here in this point in the program. Because either this test failed, which means that max is greater than or equal to number, or inside this if statement, we set max equal to the value stored in number. So at this point, the value for this assertion is always. The last one to discuss is this assertion immediately before the return statement. Think about it for a moment. See if you can figure out what the value will be always, never, or sometimes of this assertion. Are you surprised? Sometimes. You may have thought it would be always. But what if the user types in initially the number -3? So max is set equal to -3. When we enter into this while loop, number is not equal to -1, it's equal to -3. So we enter the while loop. If number is greater than max, max equals number. Well, they're equal to each other, so this is skipped. Is max greater than or equal to number? Yes. Type a new number, or -1. And the user types in -2. So then we jump to the top of the while loop and test to see if the value in number is not equal to -1. That statement is true, so we continue with the loop. If number is greater than max, is number greater than max? -2 is greater than -3. So we are going to assign max the value in number. So max becomes -2. At this point, we're going to prompt the user again for a number. This time the user types in -1. So when it comes back to the top, number is not equal to -1, fails, the test is false, so we immediately jump to the statement following the while loop. So at this point, number has the value -1, but max has the value -2. So, is max greater than or equal to -2? Sometimes. Depends on what the user types in. So in this way, our sentinel, the way that we coded our sentinel, doesn't allow us to guarantee that max is going to be greater than or equal to the value which the user typed in into number. If we were to add the validation code shown here, we would now be able to make the assertion about max that we would like to have made in the previous slide. So this validation requires that the user types in a positive number for the initial value for the variable number. So the prompt is now inside of a while loop that says type a positive number. If the number they type in is not positive, then we will prompt again and again and again until they type a positive number. The test will fail. We move to the statement immediately following the while loop. So now, since the initial number was not negative, when the user types -1, we are certain that the -1 that they type in to signal the sentinel to stop executing the program, we are certain that the -1 is less than whatever the value is in the variable max, and therefore we are able to assert that after this while loop occurs, max is greater than or equal to whatever value is stored in number. So the assert structure in Java, or the assert statement, is a statement that must be true for the program to continue to execute. If it is not, so if the assert statement is false, then the program will stop and output an error message. This is very useful in debugging. You can do the same thing with if statements. However, it's so common to do this for debugging purposes that Java has built in, as well as other languages do too, but Java has built in the assert statement to help with the debugging process. So the assertion statement has the following syntax: assert, space, and then some Boolean expression that should evaluate to true. An example would be assert n is greater than or equal to limit. So if this is true, we will continue to execute with no effect. However, if this is false, then the program will stop and display an error message. So it would be pretty bad if we were to write a program like, Microsoft Word, and in the middle of the program, it comes up and says, an assertion failed exiting. We wouldn't want that. So industrially developed programs do use assertion checking, but what happens is in the IDE, we turn assertion checking off. So these checks can be enabled or disabled. These assertion checks are disabled when the software is distributed to customers. To turn on assertion checking and be able to use this in your programs to debug, in IntelliJ, you have to add the -EA flag to the VM arguments. So you go under Run to Edit, Edit Configurations, and then add the -EA flag to the VM arguments. It looks something like this, depending on what platform you're running on. So this is inside Run, go to Configuration, VM Options, and you type in -EA. Then apply and not cancel, apply and OK. This would turn on assertion checking, so you could type in assert followed by some Boolean expression, and your code will stop and display an error message if that assertion fails. So a new expectation that we're going to place on you is we expect that you're going to comment your methods to indicate appropriate valid values for parameters. So this is referred to as preconditions. It states the conditions that must be true before the method can be invoked. So for instance, if you have a method that is going to take the square root of some set of numbers, it would be true that the precondition for that method is whatever number you wish to take the square root of must be greater than or equal to 0. A postcondition tells what the state is going to be after the method runs, or what will be true after the method runs. Pre- and post conditions are typically shown using comments above the method. So in this case, computes the square root of a number is the description. Precondition, integer parameter must be greater than or equal to 0. Postcondition, returns a double representing the square root. That completely documents this method and tells us what it is going to do, what it requires as a precondition, and what the status of the output will be. It's great to tell programmers what you intend for the precondition to be, but better than telling them and then assuming that they do what you said is to check and make sure that they have appropriately passed any preconditions that you've set. So any method that you write should verify any preconditions that are necessary to be set. To make it a little more clear, what we're saying is, even though you've said, okay, to be able to take the square root, the number passed should be greater than or equal to 0, your method should be able to handle someone passing it in a -2. It should be able to gracefully either display a message saying no negative numbers are allowed to be used, or some other situation, or assume that the value is 0. There must be some way of handling a violation of the preconditions. And there are several ways to go about this. One is to return some error value, commonly like a -1 or a 0. Another way to go about it would be to throw an exception. We'll talk about that later. Another way would be to use an assert statement or a system.exit to stop the program from running. So here's an example of a method with a precondition that can gracefully handle a violation of the precondition. This should look familiar. This is the encode method that implemented the Caesar cipher. There we go. And it clearly states the shift amount is to be between -26 and +26, exclusive. However, the first couple of statements inside this method check to make sure that that precondition is valid, that it's not been violated. If we find that shift is less than or equal to 26, or sorry, less than or equal to -26, or greater than or equal to 26, we will throw an exception. You may have noticed in the last program there was no post condition stated. That's because the post condition is obvious and was only the given return value. In this case, it's often left unstated because, as I said, it is obvious. To eliminate some of the variation of how different people go about commenting and documenting the pre and post condition for methods, we use JavaDoc comments. So this is important. You're going to be expected to use JavaDoc comments to document all your methods starting with programming assignment 7. And be careful with the JavaDoc comment syntax because it's a little different than the general comment. So typically, a general comment, // or /* followed by backslash, or followed by */ with the comment in between the stars, are ignored by the compiler. And we use these to document internal workings, and this is strictly for someone looking at the source code. The only people who really need to read these are others who are going to be working on this particular method or class. However, JavaDoc comments are written by /** and then terminated by */. So it's a minor deviation in syntax, but IntelliJ actually makes it nice. So if you begin a JavaDoc comment using /** and then press enter, it will actually expand it and fill in the rest of the syntax for you. Just be careful and make sure that you do it correctly. These are different from typical comments because the compiler doesn't ignore these, it uses them to produce JavaDoc documentation that is displayed by the IDE. So for more information on this, you'll see it again in Zybooks 5.13. So you are required, starting with Programming Assignment 7, to use JavaDoc comments to comment method headers and class headers. So where we have been expecting you to simply use traditional comments to comment your methods, method headers and class headers, now you're required to use JavaDoc comments to comment the class and method headers. Provide information on how to use the method or class along with any pre or post conditions. JavaDoc comments, unlike regular comments, are not intended for those who are going to be upkeeping the method or class, though they can be helpful to them as well. They're primarily intended for people who are going to be using the method or class. So if I was to distribute this method on GitHub and allow other people to make use of it in their programs, they would look at the JavaDoc comments to understand how to employ it in their own program. So here is what the JavaDoc comment would look like for our Caesar cipher program. Notice the syntax, and notice that each of the lines begins with a star. So we also have encode. So we write a description, followed by special keywords to designate that this is a parameter for the method, the name of the parameter, and a description of it. Same thing for the other parameter, shift, and then also one for the return value. Again, every programming assignment after programming assignment 7 and also programming assignment 7, we expect you to use JavaDoc comments to comment both the class headers and method headers. So if you have any questions about style guidelines for CS1101, remember to go to course resources on Brightspace and look at the style guidelines document. So from this point forward, for each of the programming assignments, there will also be an assignment in the assignments folder on Brightspace. You don't have to turn anything in. This is simply a place where we will assign your grade, and you can find supplementary information about the programming assignment if there is any. So here's some general guidelines on where to place comments. Top of a class, always. Above each method, always. Both of these using JavaDocs. With each variable or constant declaration, most of the time. Above loops. If it's a very, very simple loop, you may get away with no comment, but typically if it's a loop of any complexity, yes, we would expect a loop to be commented. Above decision statements. Again, depends on how complete the logic is and how complex. So if it is readable, then it may not be necessary for a comment to occur above a decision statement. However, if the decision statement is complex at all, yes, comment it. Make it clear what it does. Make sure all comments are useful. Don't have too much information, and definitely don't have too little. Give enough information that someone of reasonable ability can read the code and understand what it is you intended to do without having to labor over it for days and try to decode your algorithm. So here are 3 bad examples of commenting. Notice in the code, no comments. Yep, that's really bad. Here, better, but still pretty bad because the comments are mechanical. You're explaining to me how Java works. I can read Java. I equals 0. I understand that's an assignment statement. I don't need your comment to tell me that. So comments are not to explain Java syntax or the mechanics of the Java language. That's bad commenting. Over commenting. This is still kind of bad. So we're going through and explaining every detail of the code rather than expecting someone to make simple inferences. So this would still be considered bad commenting because of how disruptive it is to the flow of the program. So this is a bit better. Here we're explaining what the code does without over-explaining and without being mechanical in our explanation, not explaining the Java language or the syntax. So this is what we would expect, something that just says this code below computes the average of the first n elements of the score array. That's a functional description of what the code does. Whether or not it actually works, that's a different story, but this communicates what the code is intended to do. A little more on style. When you're dealing with methods, make sure that you describe what the method does, and you should describe what each parameter does as well. Remember, these descriptions that we're talking about are using the JavaDoc format for pre and post conditions as well as the description. And don't have too many parameters. Don't have parameters that you don't need. If you can derive the value from other parameters, do so, unless it increases readability. So don't unnecessarily pass parameters to methods. Keep methods short. Somewhere around 30 statements. Less than 30 statements would be better. Methods should be small, compact portions of a program that are readily reusable, not a large section of the program that you have relegated to a method. So keep them short, somewhere around 20 to 30 lines. 35 is getting a little high in my opinion. Also, watch the line length. Don't go above 80 characters. There is a grace amount of 20, so if you go above 100, you're going to get point deductions, but typically stay less than 80. Use the visual guide in IntelliJ for help. The reason here is printability. Also, because it's difficult to read very wide lines of code. It's better to keep code compact into the left side. Use blank lines effectively to show logical separations in the code. Definitely leave blank lines in between methods and above the JavaDoc comment area above your method. Indent your code properly. This should be super easy because IntelliJ has built in an auto format, and it's very good. Make sure you use the auto format and don't mess up the indentation of your code. That makes it nearly unreadable. Remember to only define a single scanner, because if you define more than one scanner, you're going to crash Zybooks, and we've warned you about it several times, so do not declare more than one scanner object for system.in. Define it in the main and pass it as a parameter to any methods that need to make use of it. Finally, make sure that your variable names as well as your method and constant names are very meaningful. So all the identifiers that you use in your program, make sure that they are very meaningful and descriptive. Make sure that they increase the readability of your program. It should be that a variable name is almost a part of the documentation. So if I read through the code and I'm reading and seeing the variable names, it should be self-explanatory what this code does. And that's accomplished by using descriptive, well-chosen identifiers for methods, variables, and constants.